Now, just as a quick review, in terms of what we were doing last time with this stuff. So, oh, no, not that one quite yet. This one. Okay, we want to take a look at crosswordFormation. Oof, just looking at this, seeing this huge wall of all these permutations, oh, it makes me feel like we're going to have to do something about that. So that's going to be our goal for today. But before we get into that, let's just sort of review how we were going through this, what we were doing here. And yeah, Rainbow, hey, I'm a beginner too, so that's the thing. Anyway, continuing with this, basically the idea is we're trying to do this crossword problem, right? We're trying to, given 4 words, we're trying to sort them out in such a way that they form a crossword, you know, and an important part of that is they all have to intersect. All the words need to intersect, 4 pairwise intersections, and they can't be too close. So there needs to be at least some area in the middle here. So each of them needs to be spaced out like by at least 2 characters. Okay, so our way of doing that was basically just very systematic. We broke it down and we pretty much said, so if we want to find the intersection between 4 words, let's first find the ways we can find the intersection between 2 words, right? So we had this right here, first of all, right? So H word 1, V word 1. So we had a horizontal word, we had a vertical word, and we just want to find the ways that they can intersect. So we're just going through each of those in a for loop, just looking at every single one of the characters. Well, not quite every single one of them actually, because no sense in checking these 2 characters because the first word wouldn't be able to connect with either of these and at the same time leave enough space for the second word. So we won't bother checking those. And similarly, we won't bother checking the last 2 characters of the vertical word. Okay, so basically we'll go through the nested for loops over here. We'll check to see if the characters at those indices are going to be equal. And if they are equal, so let's say we find the intersection between like the R over here. Well, basically at that point we say, oh, okay, we found a way for these 2 to intersect. So now let's get another word in the mix, right? So we do another set of for loops over here to correspond to the position of the horizontal word where this other vertical word is going to intersect. So this is H word 1, V word 2 now, as opposed to H word 1 and V word 1 over here. Okay, from there we check to see if those 2 match up. And note that for H word 1 now, we're not bothering to look at any of these, okay? We're starting after this one, not just after this one, but like a bit after it, right? So it's not too close. We know, or at least we're structuring this in such a way that we're making the assumption that this will be the first word and this will be the second word. And that's why we have all these permutations up here just in case, well, what if this one was the first one and that was the second one, right? So basically that's why we need all the permutations, because we're basically just assuming, okay, let's say the first one you see, that's the first horizontal word. The second one you see, that's the second horizontal word. Third one you see, that's the first vertical word, etc. So basically the idea is that we're just assuming what the order is going to be, and then we'll just rearrange and look at all the possible orderings. That's the idea. Okay. So if we get to this point here, if this if ends up getting passed, then we have 3 connected words. We have the first horizontal word and we have the 2 vertical words, all connected. And all we need to do from there is basically fit in this last word here. But keep in mind, that's still 2 nested for loops. And the reason is because we don't know where vertically it's going to connect up, you know, like maybe it's these 2 letters, maybe it's these 2 letters, who knows? And we also don't know like which 2 letters from this word is it going to connect with, you know, maybe it's like the H and the N or something like that. So we need to check both of those. And we also need to check as we're putting it through here that it matches up not just with, let's say, the O over here, but also the E. So that's why there's more stuff in this one. There's also this extra little bit here because we're keeping track of the horizontal offset and the vertical offset. Horizontal offset referring to how far apart these 2 words are, and the vertical offset corresponding to, like, you know, this one starts up here, this one starts down here. So anytime we're going through these, the index that we're looking at, the character of the word formation, should be exactly 2 greater than the index in the word square. So that's basically the idea behind that. That's why I have the vertical offset. And we could probably change the boundaries of I think this loop over here to accommodate for this, just to make sure that it is actually getting to a point where it's finding this. The thing is, we're doing an if here anyway, so I don't know if it's really worth it. Well, it probably is, because it would actually stop the loop a little bit earlier. That's one of those micro optimization things that I wrote about in the article today, so check that out if you want. Anyway, we're going to continue with this. Yeah, I mean, it's pretty much done, right? Like it's passing all the tests. It got us the win yesterday. But there's one aspect of it that I don't really like, and it's this, all this junk up here. Come on, man. You've heard of this principle. right? We want to keep it dry. We want to don't repeat yourself. That didn't come out right. Anyway, don't repeat yourself is this principle we want to be following. I think I'm repeating myself here. It looks like I'm repeating myself. So maybe I should not do that. Okay, how are we going to not do that? Well, basically, I want to come up with some way to generate all the permutations. Now, this is something we've done before. We've done this in a few different challenges in the past. We've generated permutations before, but not that well. I think we could do it in a kind of a smarter way. So let's take a look at this. This is a really, I'm told anyway, this is a really common algorithm for finding permutations. When I was looking on Stack Overflow about this, a lot of people were pointing towards Heaps Algorithm. Now keep in mind, Heaps Algorithm is not the only one. This is another really cool one. I mean, I thought this was so cool looking at the, what do they call this thing? It's like the, yeah, Permutation. I'm not sure if I'm pronouncing that right, but what a concept, right? I mean, this is a fascinating article if you have the time to go through it. Really neat, just the geometry of it is super cool looking. But anyway, we're not here to talk about that. We're not here to talk about permutahedrons or the Steinhaus-Johnson-Trotter algorithm. We're here to talk about Heaps algorithm. So basically, Heaps algorithm is kind of summarized with this image over here, but I kind of pointed this out yesterday. If you just tried to understand it from the image, you might still be a little confused because it's kind of going all over the place. It's a little tough to pick out exactly the pattern that it's using here. So let's read about it. Now, I have to say, before we go any further, I have not implemented this. This is not something that I have done. I've never done one of these, okay? So this is gonna be a new experience for me. I'm gonna be basically learning this on the fly right now. So if I make any mistakes, if it seems like I'm having trouble understanding anything, if you can help me out, appreciate it. If you have any questions, definitely feel free to let me know. But basically, we're gonna try to learn this thing together. Should be fun. Okay, so let's see. Heaps algorithm generates all the permutations of n objects. The algorithm minimizes movement. It generates each permutation from the previous one by interchanging a single pair of elements. Okay, so I think that was pretty obvious by the diagram over here. Every time we move from one to the next, we're doing one flip, right? We're interchanging. We're just switching the position of exactly one pair of elements here. So that's basically the idea. Okay, so we do one at a time, and we basically go through each of the permutations exactly once. We don't repeat ourselves with this, which is nice. So the order of it might seem a little strange at first, but okay, I think if we wanted to sum it up geometrically, we would say it's a Hamiltonian path through the permutahedron. I think that's what it means. Anyway, okay, so basically, what else does it say? The other n-2 elements are not disturbed. Right, okay. In a 1977 review of permutation generating algorithms, Robert Sedgwick concluded that it was, at the time, the most effective algorithm for generating permutations by computers. So this is, you know, pretty state-of-the-art for 1977, not bad. The sequence of permutations of n objects generated by Heaps algorithm is the beginning of the sequence of permutations of n+1 objects, so there is one infinite sequence of permutations generated by Heaps algorithm. Oh, okay, it's in the OEIS. By the way, if you guys are not familiar with this, the Online Encyclopedia of Integer Sequences, which I thought it was going to actually take me to, this is a super, super useful resource. Definitely, I've used this in a lot of computing problems. Generally, if you're noticing patterns in the outputs, but you can't quite place them, this can be a really, really helpful reference. Sometimes it'll give you formulas for how to actually generate that sequence. So definitely, if you're not familiar with this, get familiar with it. It's just oeis.org. And even if you're unsure about some of these, then you can say like, well, I don't know what the third one is, but I know these other ones, and you know, it'll search for it. And oh, okay. Sequences wildcard are unavailable for a few days. Okay, sorry about that. Forget I mentioned it. Anyway, the point is, so Heaps algorithm. let's look at the details of it. So suppose we have a permutation containing n different elements. Heap found a systematic method for choosing at each step a pair of elements to switch in order to produce every possible permutation of these elements exactly once. Yeah, okay, so that's pretty much what we were talking about. Let's describe Heap's method in a recursive way. First, we set a counter I to 0. Now, we perform the following steps repeatedly until I is equal to n. Okay, so that sounds a bit like a for loop to me, right? Let I be assigned the value of 0, go until I is less than, go while I is less than or equal to n, I guess. No, while I is less than n, because we want to stop, I guess, when it's equal to n. And n is the number of elements in the permutation. So in this case, I guess it would be 4. Okay. We use the algorithm to generate the n-1 factorial permutations on the first n-1 elements, adjoining the last element to each of these. Okay, yeah, it makes sense. I mean, that's pretty much how factorial is sort of defined, right? I mean, like 4 times 3 times 2 times 1, right? So like we could fix the last element and then look at the number of permutations in the remaining 3, fix the last element of that, look at the number of permutations in the remaining 2, you know, etc. So it's kind of recursive in that regard. And I guess we are going to get a recursive algorithm in just a sec, so we'll take a look at that really soon. But where were we? So this generates all the permutations that end with the last element. Then if n is odd, okay. If n is odd, so we're going to have some kind of conditional in here. If n is odd, we switch the first element and the last one. While if n is even, we can switch the ith element and the last one. So basically there's no difference between n being even and odd in the first iteration because the first element is the ith element. Okay. We add 1 to the counter I and repeat. Okay, so that would also be part of the for loop, the I++ part of it. Okay, great. In each iteration, the algorithm will produce all of the permutations that end with the element that has just been moved to the last position. The following pseudocode outputs all permutations of a data array of length n. So let's take a look at this. This is pseudocode, so this isn't written in any particular language, but it's nice because it's sort of outlining the algorithm and the sort of steps we would want to take. So basically we've got a procedure, it's called generate, and it takes in 2 inputs, 2 arguments here. So n is an integer, a is going to be an array of any type. In this case, it looks like it's an array of length 4 containing strings, 1 character strings. Okay, so we're saying if n is equal to 1, then just output a. Okay, so I guess n is referring to like the number of elements, right? So if n is 1, just output a. Give us whatever a is at that point. Otherwise, do this. We'll do this for loop. So this is what we were talking about. I is going to start at 0. I is going to go all the way up to n-1, and then I++ over here. Okay, and then over here, we're going to generate... Okay, generate is the name of this thing over here. So we're calling this function. That's where the recursiveness is coming in, right? So within the function, we're calling itself. That's also why we want to start it with an if statement, because otherwise this would go forever and it wouldn't just be an infinite loop. It would be like an infinite recursive loop, which would max out the call stack, and it would be very bad. Bad things would happen. Okay, so basically we don't want to do that. We want to have some endpoint here. How do we know it'll actually end? How do we know it'll eventually just output a? Well, my claim is eventually it'll hit n equals 1. And the reason is because when we call generate again, we're not just calling it with the same n value, we're calling it with n-1. So it's kind of like we're subtracting 1 off of it. And then we're calling it with the same array. But keep in mind, we're then, after we do this, after we generate, you know, this, then we're going to do another if statement, and this is going to be about whether or not n is even or odd. Remember, if it's even, then we want to switch the current element with the last element. If it's odd, we want to switch the 0th element with the last element. So yeah, that's basically the idea. And that's the end of the for loop. And then after that, it looks like we're calling this again. We're calling generate. Okay. I think I know why that is. I think it's because of this over here. Yeah, because it's basically saying, I was wondering this earlier, because like, why didn't they just say I is less than n, right? Because it sort of says that, where was it? Yeah, it's going to perform these steps repeatedly until I is equal to n. I think the reason it's done this way is so that after the last one, it doesn't do this stuff. I think that's the idea. Yeah. There's also a non-recursive way to do it, but yeah, recursive is probably fine. I think that would be good. So yeah, any questions, comments, or concerns on that? I think that's probably pretty good. I mean, if we wanted to, we could sort of jump into it and try to take a look at exactly how it's going to run. So let's just do a sort of a simplified case, and let me choose a pretty sick color for this. Okay, cool. So let's say we've got n, we've got a, and what else have we got? I guess we'll put in I as well. I'm not exactly sure what this table thing is going to end up looking like, but let's say we're trying to find the permutations of an array containing x, y, and z, okay? And just for the sake of simplicity here, I'm not going to put in, you know, what do you call those? Quotation marks. Oh boy, I almost called them parentheses. Anyway, cool. So maybe these are variable names, maybe it's, I don't know. But the point is, this is x, y, and z. Okay. So we start out, n is going to be 3 because there are 3 elements here. So we're going to say n is 3. So right off the bat, we call this thing and we say, is n equal to 1? No? Okay, so we'll go into the else here. So what are we going to do? We're going to say I is assigned the value of 0. Yeah, okay. Our a right now is just x, y, z. So nothing changed there. All right, cool. And then what do we want to do with that? Well, basically, we're just going to call this thing, right? Actually, I don't want to really mess up the code, but yeah, okay. So we're going to call that thing. We're going to generate with an input of 2, an array that's the same. Okay, so now n is 2, array is the same exact thing, x, y, z. I don't know how far we're going to go into this. We'll find out, but anyway. Okay, so we've got this now. Is n 1? No, it's not 1. So we're going to start this again with an I value of 0. The first thing we're going to do in here is called generate again with an n value of 1 now. Our a value, x, y, z, still hasn't changed, okay? It's the same array as always. Okay, so now we get to this point where we say, is n 1? Yeah, it is. So we're actually going to output this thing. So I don't know where to put this. Maybe I'll just like start a list down here. So x, y, z. Okay, cool. So we don't have any I values for that. We're done with that one. So we'll move on from that one. It's been executed. So now we're back to this. So we've actually, wait. That is skipping a step. I forgot to do this part. So if n is even, so n is 2 right now, so that is even. So we're gonna swap a at I with a at n minus 1. So what's a at I? Well, I is 0, right? So it's the 0th element. N minus 1, well, that's, yeah, I guess n is 2 in this case. So n minus 1 would be 1. So we'll switch the x and the y. So we'll have y, x, z. Okay? Great. And then we increment I, so it's 1 now. Cool. And this is still for an n value of 2. All right, great. So there's our array. What are we going to do next? Well, we're on to our next iteration. We have an I value of 1. So what do we do with that? Well, we're going to call generate again with now this array and with an n value that's 1 less. So it'd be 1. It will trigger this part over here, which is going to put this into the books, the record, right? Okay, so now we have a as being this array. Great. And, you know, that instance of the call will end, the one where n is 1. So I didn't bother writing it in here, but it'll produce this in our list. Maybe we'll continue just 1 or 2 more steps here. So basically the next thing to do is, yeah, what is the next thing to do? Another swap, right? So we say, okay, well, wait a minute. Isn't n still even? Or is it not? Yeah. N is even now, right? So it's a at I. Oh, yeah, n is even, but I is different. Okay, cool. That's fine. All right, so basically, we're going to do this again. So it's a at 1, which is going to get swapped with a at n minus 1, which I guess would just be a at 1. Well, that's kind of weird. Wouldn't that just be calling itself then? Or sorry, swapping with itself? Won't that not swap? Unless I've misunderstood something here. Maybe that's the case. Yeah. Unless the n minus 1... Unless I'm doing that part wrong. That's strange. You know what? maybe we should just try it out. Yeah, because otherwise, if we're just swapping the one character with the one, aren't we just going to get the same thing? Oh. Yeah, I mean, I was going to say, like, yeah, we'll get the same thing, but yeah. Okay, anyway. Oh, wait a minute. Okay, sorry, guys. I messed up here. So this actually would have stopped. It wouldn't have actually got to this next one because it would have noticed this over here and said, we're not going to iterate that anymore. So the reason this would have been in here is not because it would have done another iteration with this. It's because it would have done this down here. Okay, sorry about the confusion on that one. Glad we sorted that out. All right, let's continue. So basically, continuing with this, now I think we've finished. Yeah, haven't we finished our loop where n is 2? I think we're done with that. So we can move on. We'll go back to this one up here where n is 3. Now we're going to do another swap. Okay, so n is 3, that's odd, which means we're going to swap a at 0 with a at 2, right? Yeah, because n is 3 now. So that means the y and the z we're going to switch. So we'll get z, x, y. Okay, good. I'm glad we sorted that out. So we do that. And then it's going to reach the end here, and it's going to go on to the next iteration where I is going to be 1 now, because remember I was 0 in the last time that n was 3. Okay, cool. So we'll continue with this, and basically the idea is that now we're going to call this, right, generate with n minus 1. N would be 2, a would be this still, z, x, y, and I would start at 0. Yeah. And what's that going to do? Well, it's basically just going to say generate with an n value of 1 and an a value of this, which is going to mean that this zxy is going to get entered in our list of permutations. Cool. All right, so that's great. I feel good about that. You should feel good about that too, if you want. It's up to you. Anyway, the point is, this is looking good. This is giving us an idea of where this is going to go. It's going to continue. We're getting permutations each time. They're all unique. We're only going to see each one of them once. So it looks like this algorithm is working. It's, maybe a bit tough to understand these recursive algorithms. I mean, if I had maybe a better visualization of like what the call stack would look like and something like that, then maybe that'd be more effective. But anyway, hopefully it's making sense. I think we can trust this algorithm. So let's try to implement it. The question is, how are we going to implement this thing? I mean, there are a few ways we could do it, but okay, maybe we should try. Okay, let's try just kind of freestyling it here. Okay, so crosswordFormation, we'll put it right in here before the returns. So basically, we'll make a new function, and they were calling it generate, so maybe we'll call it generate. Yeah, that's probably fine. Function generate. And what does it take in? It takes in 2 inputs. One of them is going to be the array, which I guess they were calling it A. We might as well keep calling it A. And then the other one is going to be N. We might not know what N is from the beginning, so let's just say by default, it's going to be a dot length. Okay, so this is like an optional argument. Right? So the idea is that when we do this, let's just do a quick console log of A and N. And I'll just say return generate. And it's probably just going to return null here. Oh, length of undefined. Yeah, I should probably call it with at least something. So let's say words, I guess. So generate with words as an input returns nothing because there's no return statement here. But what we get is a log of this and the length of it. So notice this thing, n is assigned the value of a dot length. That would be the same as doing something like this. So we'd say if not n, then n is assigned the value of a dot length. Okay, so same thing by just putting it up top right here. Optional variable. So basically if they don't call it, or sorry, our optional argument, if they don't call the function with that argument, then it's just going to give it this default value over here. Okay, but we could also call it with some other argument like 100, or I guess I typed in 1,000. But anyway, the point is we can give it that argument. It's just if we don't give it that argument, it'll make an assumption and give it what it feels is most appropriate, which is based on what we type in here. Great. Okay, so we've got this. what do we want to do with this now? Well, basically this is the thing that we want to use for our permutation generator, right? So maybe I'll do something like this, const permutations. It's just going to be this array that's going to start out empty, and it's ultimately going to be the thing that we want to return at the end after we make a quick call to generate. Cool. So what do we want to do with this? Oh, and generate with words? Yeah, words. Cool. Actually, maybe just to begin, let's just do 3. Let's make it X, Y, and Z. Yeah, cool. Just like we had in the example a minute ago. Okay, so we want to do our generating here. What do? We say, well, if n is equal to 1, then we're going to do permutations dot push A. Yeah, A. Cool. Else, we're going to do something else here. What are we going to do? Well, more specifically, I think it was this, right? For let I be assigned the value of 0, I is less than n, I plus plus. And what we want to do here is basically, first we want to call this function, so generate, yeah, with the same a value, but with an n value that's 1 less. After that, we want to do our swap, right? So we'll say something like if n mod 2, and basically if n mod 2, well, there are only 2 possibilities here. It'll either be 0 or it'll be 1. If it's 1, then this is going to return true. If it's 0, it'll return false. So basically we'll put an else on this. So true would mean it's odd, false would mean it's even. Let's try to remember what it was. So it was that we want to take a at some index and a at some other index, and we basically want to swap these, right? So I'm going to use this destructuring assignment to swap them, and I'll do the same thing down here. Okay, I guess we could probably also like write a function like that to swap the elements, but who cares? Okay, so I think n minus 1 was one of them, right? It was, one of them was where we swapped the current element. So it was I. Yeah, just I. And the other one was where we swapped the 0th element, but I don't remember which was which. So maybe we should check on that. So where was it? If n is odd, we switch the first element and the last one. Okay, so if it's odd, oh, got these mixed up. All right, there we go. So a at n minus 1 and a at I. Hey, knock it off. Okay, and then this one, a at 0 and a at n minus 1. Cool. Yeah. Is that it? I don't know. Is that what we want? Let's see if that works. Whoa, that's totally not what we want. Wow. Okay, so why did this happen? Well, I think it was because we're pushing a every time, right? So basically what we're pushing into the array is another reference to the array a, when really what we want is a new array that has the same elements as a. So I'm using an array literal to instantiate a new array. What am I putting in it? Well, I'll use a spread operator to take just the inside elements of array A. So it's not an array containing array A, it's an array containing the elements of array A. In other words, hey, it's a deep copy. All right, let's run that and we'll see if that makes any difference. Okay, so we get x, y, z, y, x, z, z, x, y, x, z, y, y, z, x, z, y, x. Folks, I think we have it. I think we've done Heaps algorithm. What do you think? Did we do it? Let's see. You know what? I'm looking at this and I'm thinking we could probably give this another index. So let's say const swapper is going to be n mod 2. And if n mod 2, yeah, so if it's odd, that'll be 0. Otherwise, it'll be I. Yeah, cool. Because that way, we don't need to worry quite as much about this if-else statement. We just say swapper. And that's, I think, it, right? I don't think we need to do anything more than that. Let's try running that. Let's see if it works. Yeah, seems to be working. Okay, cool. So that's giving us our permutations. Yeah, what else could we do with this thing? I guess we could probably generate all the permutations of words. So yeah, there we go. There's a whole bunch of them. Okay, nice. Well, that's pretty not bad. You know what? Yeah, okay, so I think this is probably pretty good. I think we could modify this in such a way that it's going to work a lot better. So we could do something like, okay, instead of all this junk, maybe we could do something like return permutations dot reduce. No, permutations dot map. Yeah, I'll just say W for words. That'll get mapped to do crossword of W. And then we want to reduce this. Say A and B will get mapped to A plus B, just to sum it up. And we'll see what we get from that. And we're not getting anything because we're doing this up here. So let's maybe not do that. All right, let's try to run this. Oh, yeah. Okay, folks, feels pretty good. I like that. I like this a lot better. I think this is a big improvement over what we had before. Let's just make sure it passes the hidden tests. And then, okay, great. It's passing the hidden tests. But I'm not done. So check it out. There's another change I want to make to this thing. I have an issue with this. So I think this is considered an anti-pattern. I think this is considered something you're kind of not supposed to do. Because I have this array here that I'm filling up with this function over here, right? Like I'm saying permutations.push for something that's like outside of this function. It's not exactly self-contained. I don't super like the way it's doing this. I would prefer for it to maybe be like returning something that I can then iterate over. That would feel a little more comfortable to me. So this is an exciting moment. We're about to do something totally new. This is completely new to me. This is a concept that I've seen before. And, you know, it's one of these things. Hey, guys, let me know if you've encountered this before, okay? You see this concept coming up, you know, or like the name of something, and it just kind of stresses you out to hear it, you know? Like for me, one of these examples used to be hash maps or hash tables. I never quite knew what it meant, and because of that, it would really stress me out when people would mention it, because it's just like, not really comfortable with that, you know, it's outside of my comfort zone. So now, I mean, what I found is like, I studied hash maps, I learned what they were, and now I feel great about them. My confidence is way better. So when I hear them, I get excited, because it's like, yeah, that's something I know. So just wanted to mention that because there's this concept that's been kind of nagging at me, okay? There's this concept that I keep seeing, and I always feel a little uncomfortable with it. So I want to make that no longer the case. I want to actually start to understand this thing. Let's dive in. The concept I'm referring to is generator functions, okay? So I don't know if you guys have seen this before. It's where you have the function and like a little asterisk. It's a generator function. I haven't really had a good understanding of what these things are all about. Recently, I've been trying to take a look at a couple articles and stuff like that. But I wouldn't say I'm an expert of this concept. I haven't actually built one yet. I haven't attempted to actually make a generator function. So I'm kind of curious. I want to know what it's like. Let's give it a try. So I'm looking at the docs here. I want to get an idea of what it's all about. So let's take a look at the description. Generator functions. Generators are functions which can be exited and later re-entered. Okay, so right off the bat, mind-blowing, right? Normally a function is something that gets executed and then it's done, right? I mean, this one in some ways is a bit exceptional because it can sort of keep going, like it keeps generating more of these because it keeps calling itself. But as soon as it finishes with that last call, it's done. Right? It's not like we can jump back into it at a later date and have it remember the state that it was in. So this is a big deal. Okay, their context, their variable bindings will be saved across re-entrances, which means that we run this function And, you know, maybe it's got some variables in it. Maybe it's got like x is assigned the value of 5. And we want to, it'll just return x. And then the next time we call it, it'll add 2 to x and then return it again. It'll be 7, for example. And then the next time we call it after that, it'll add 2 again and it'll return 9. You know, this sort of thing. So JavaScript is really great for these kinds of things, right? Functions that sort of have these hidden memories that they remember. Like, what do you call those? Like immediately invoked function expressions, you know, closures, that kind of stuff. They tend to hang on to like hidden scopes almost, right? So this is very much within, it's like this is in line with the JavaScript brand, right? It's in line with the kind of flavors we expect from this language. So, okay. Calling a generator function does not execute its body immediately. An iterator object for the function is returned instead. When the iterator's next method is called, the generator function's body is executed until the first yield expression, which specifies the value to be returned from the iterator, or with yield star, delegates to another generator function. So that sounds a bit like a recursive thing, like what we were doing in our function over here when we call this generate thing. If this was a generator function, we would probably want to yield star this, but we'll find out. So we'll continue with this. Okay, the next method returns an object with a value property containing the yielded value and a done property, which indicates whether the generator has yielded its last value as a Boolean. Calling the next method with an argument will resume the generator function execution, replacing the yield expression where execution was paused with the argument from next. Okay, so that part we might not get into today. But let's just finish this up. So a return statement in a generator, when executed, will make the generator done. If a value is returned, it will be passed back as the value. A generator which has returned, I don't know why they didn't code block this one, but anyway, it will not yield any more values. Okay, so I guess that's like the done property would be set at that point, right? Yeah, it'll make the generator done, so that's why I won't return any more values. So, okay, they've got some examples down here, but really, I think we should probably just try to work with it ourselves. So they have this nice, helpful little window over here. Let's take a look at what they've got over here. So function with a star, it's called generator. That's how we know it's a generator function. Sorry, the star is how we know it's a generator function, not the name. I think we could call it whatever. In fact, let's try calling it whatever. And that means we'll have to be consistent, right? So if this is called whatever, so is this. But notice we're saying yield I, and I is just our input here. Then after that, yield I plus 10. Okay, so here we're saying var, could we use let? I'd prefer that. Let gen be assigned the value of whatever with an input of 10. Console log gen.next.value, and then console log gen.next.value again. Let's run that. Notice we're getting two different outputs despite the fact that we're console logging the exact same thing. So the way this is working, our generator function, is it's running up to the first yield and then stops. And then it'll run to the next yield and it's going to stop there again. What would happen if we tried to throw another console log on here? So we'll do gen.next.value. Whoops, I did a control R. Oh, God. Okay, let's try not to do that again. That is a very unfortunate key binding, but oh well. Okay, cool. So 10, 20, nothing. We got undefined. Okay, well, I wonder why. Well, probably because there are only two yields here, right? Could we throw in another yield? Yield 5. Oof, almost did control R again. Okay, cool. So if there's another yield, then that's fine. I'm curious. We're doing .value, but what else do we have in here if we just want to look at next? Okay, so we've got value 5, done, false. Let's do another one of these. So console.log of gen.next, and we'll run it using the button. Okay, value undefined, done, true. Okay, so this is kind of like what we're talking about down here when we're talking about the done property. So since there's nothing left to yield, it's considered done. All right, good, makes sense. I think that's all good. We could probably even do something like this. I mean, this is the difference between a traditional function and a generator function, is that these can keep yielding more and more things, unlike a regular function where as soon as we hit return, anything under that is never going to execute. For these ones, it's not that they'll never execute, it's just that they won't execute until you ask them to. So let's say for let I be assigned the value of 0, while I is less than 5, I++ at the end of every iteration here. What do we want to do for each of these? Well, we want to yield something. So I probably shouldn't call this one I if there's already an I up here. I guess we'll call this one J. Whoops. Okay. Let's put that in here. What do we want to yield? Well, let's do something like J times I. Okay, something like that. Let's run this, and okay. So now it's not done at this point, right? And maybe we should get more values in here. Yeah, dot value. Okay, let me copy this and paste it in a few more times. Let's try running this. We got 5, we've got 0, we've got 10, 20, 30. Okay, cool. So this seems like it's generating the things that we're looking for, right? We've got J times I. So basically J starts at 0, I is 10, so it's going to be 0, 10, 20, 30, etc., right? Okay, but you know, I'm getting kind of tired of doing all these console log, right? It's getting a bit tiresome. So I'm going to do something a little bit different. I want to show you something. Check this out, console.log. These things, these generator things, actually hold on. These generator things are iterables. This is really important, okay? So even though it's doing this .next thing, it's something that happens in an order, so it's an iterable. What do I mean by that? Well, we've seen iterables before, like arrays, but let's check this out. So we'll say for const, I don't know, thing of gen. Okay, so I'm just going to iterate. I'm doing a for loop that just goes across this, and it's going to console log thing each time. Let's try running that. Look at that. We get the same stuff, exact same stuff. It's just going to yield everything it can. Okay, so when we do this for thing of gen, it's just going to yield all the values. So thing is going to be like the .next .value kind of thing. All right, so we've got that in there. We could also do something like this. Maybe we'll start with a little console log of an array. Yeah, let's do it like this. So array.from gen, right? We could do something like that. Run that. There we go. Okay, we're console logging it. I'm not sure why it didn't do the for now, but oh well. Oh, you know what? It's probably because we've already gone through, we've already generated all of them, so there's nothing left by the time we get to the for. That makes sense. Okay, so we got gen in there. There are other ways we could do this as well. So just like, you know, we've done array.froms, or sorry, instead of array.froms, we've done like this kind of stuff, right? Where we use a spread operator, spread operator just to get all the elements in here. We could run that. Cool. Could we even do something like this? I'm wondering, math.max of all these things, right? Spread it out. It's all the elements in there. Let's run it. 40. That was the maximum one. Cool. So this is neat. This is really neat stuff. I like these generator functions. I think they're cool. Let's use them. Or wait, should we? Yeah, let's try it. Okay. So we've got this. I'm just going to copy all this. Well, I'm going to cut it technically. We're going to confirm that. We're going to bring this all down here. I'm going to put some numbers on these things. So I'm going to say this is going to be 1. No, sorry, 2. We've already done 1. So that's going to be 2, and that's going to be do crossword 2. Now, what else am I going to do? Well, I'm going to take this. I'm going to copy all this stuff. I'm going to put it in here now. You might be thinking, whoa, hey, 0, what are you doing, man? That wasn't part of crosswordFormation. That was part of your other function, do crossword. Well, you know what? I want to make peace between the two functions. I think they should live in harmony. So I want to try to get them all together now. All right, so what are we going to do with this? Basically, I'm not going to do this permutation things anymore. I'm not going to have this permutations thing. I'm going to have this, except let's make it a generator function. That'd be cool, right? So instead of this, instead of like pushing this into something, we're going to yield. this, just like our generator function from before. And instead of doing this over here with our generate thing, we're going to yield star this over here because this is our generator function. So we should use a star to represent it. And now, could we do something like this? Could we say, you know, console.log of an array, which is the spread out version of generate with an input of words. Let's try running that. It'll do a console log and then it's going to do all this stuff, but it's not going to know what we're talking about. So maybe I should just comment all that out for now. And we'll get it back in a sec. Let's run this. And what are we getting? Oh, yes. Okay, we're getting what we're looking for. So this is good. This is good. I'm excited about this. Check it out. Could we do the following? Could we do for const? Oh yeah, this is great. Oh, this is going to be so great. So check this out. Check this out. We've got this stuff down here, and it's basically saying, wait, hey, what? Oh, okay, yeah, cool. So we got this stuff over here, and it's like, well, we've got H word 1, we've got V word 1, but what are those things? Well, we're about to do that. So we're going to say H word 1, H word 2, V word 1, V word 2 of generate. Should I call this generate? Maybe I should call it something else. Permutation? Yeah. Permutations? Or permute? I don't know. What would be better? Permutations of words. Yeah, I think that's probably clear, right? Let me just do a quick thing. Console.log H word 2. Let's try that. Okay, and yeah, we'll just cut this out for just a sec. We'll just run that, see if it's working. Yeah, it looks good. Okay, cool. We're not getting any errors or anything like that. Actually, wait a minute. I didn't, oh wait, hold on. Yeah, I could have cut that out because I actually don't want to paste it in there. I want to paste it in here. So let's paste it in there. Now, technically this part, that's gonna go outside. Yeah, where it belongs. Okay, and then all of this stuff needs a little indentation. And this is also gonna go outside. Let formations be assigned the value 0. It'll go after the permute function, but before the big loop. Okay, so look at this. Look at all those levels of nesting. We have 7 nested for loops. Wow. And does it work? Ooh, it works. Okay, I have to say, I'm proud of this. I'm really happy about this. We've created our first generator function. It's working. It's not this. This is crosswordFormation 2. So clearly that's not the one doing the work. It's this guy over here. It's working. It's giving us what we're looking for. We're getting all the formations. Considering everything we've been through, I think the code is pretty decent. So I'm pretty happy with this. I think this is a good algorithm. I think it's a solid algorithm. As much as it pains me to see, what is this, 9 closing braces at the same time, in some ways it's kind of cool. So let's submit this one. This will be our final one for this. And oh, that feels good. I thought it would never end. We've basically been working on this task all week. But you know what, folks? It's been worth it. Because look at what we got out of it, right? We got a sick algorithm. Actually, wait. Is there one more thing we should do? Okay, this, right? Should we do this? Maybe not. It's over here. Should we try this? I don't know. I'm kind of inclined to just give it a try because we have a few more minutes before I should get going. So we'll do this and our second part of the for loop here. So while q is less than that and this. But wait a minute. No, because that'll stop the loop. Okay, hold on. Yeah, that'll stop that's no good. What I was thinking is like, unless, am I getting this wrong? I'm just trying to think, because like, okay, let me be clear about what's going on in my mind right now. So I'm looking at this over here. I'm thinking we're doing this little check to see if if the connection point, the potential connection point on the second, so between the second vertical word and the second horizontal word. So this connection point here, or, you know, this connection point over here, or intersection, whatever you want to call it. But basically, I'm checking to see if that is actually a valid index of this second vertical word, right? So like I wouldn't want to check this over here. So the reason I was going to put this up here, up here in the for loop, the reason I was going to put it there, oh, yeah, I don't think this should be an issue, actually. So what I was going to say is the reason I think we should put it here is because as soon as it finds one, like as soon as it's like, oh, there's no character here, it shouldn't go any further. There's no point in going any further than that. So yeah, okay. So maybe there's like an elegant way we could do this. So we have v offset, right? So we could say something like if q plus v offset is in word 2. Could we do that? Whoops. Let's see if that'll work. Q plus v offset in word 2, in v word 2. Yeah. This over here, and q plus v offset is in v word 2. Yeah. Is that what I want? No. Wait, what's going on? Oh, okay. The in's not working here. Maybe it's because it's a word and not an array. So if this is less than vword2.length, I guess is really what I'm trying to say, right? Okay, cool. Yeah, that's probably the best way to do it. What I was concerned about before, because like I was just saying, what we want is for this to basically break out of the loop as soon as it finds that this is no longer the case. So it sort of makes sense for it to be one of these conditions that it's checking up here. But the reason I was hesitant is because I was thinking, well, what if it happens in the other way? You know, like what if it's that that it hasn't started that word yet? But then I realized, well, that couldn't ever be the case, right? Because we already know that this one has formed an intersection point with a word that was a horizontal word above this one. So there's no possible way that that could happen. So we don't need to worry about it. Okay, that's a bit better, I think. I'm even just going to do this. So I'm going to put this thing on the next line, which means, hey, we're up to a nice even 10 of these. So great. That feels amazing. All right, nice job. Nice job, everyone. We did it. We crushed it. We absolutely crushed it. This is beautiful. This is one of the nicest algorithms we've ever written together. Thank you for being part of it. It's been an honor. Whew. Okay, let's just submit that one last time. Make sure it's passing all the hiddens. I'd be really embarrassed if it didn't. Okay, great. I can breathe a sigh of relief now. Nice job, everyone.